So today we're going to work on some application problems related to exponential growth and decay. So we're going to write and use models to solve some of these problems. All right, so let's review the two different types of exponential functions. So we have exponential growth, which occurs when a quantity increases by the same percent in each unit of time. And our exponential growth model, you might recognize it looks a lot like the model we were just graphing yesterday, where we had a times b to the x power, only now this exponential growth model, that b value is broken down into this 1 plus r, which is known as the growth factor. So the b value is going to be a growth factor in an exponential growth problem. And remember, that is where the b is greater than 1 in growth, which makes sense because you're taking some rate and you're adding it to 1. So it's going to have to be greater than 1. The A will represent that initial amount that you're starting with, whether it be number of people or amount of money or the value of something. T is the time period. You can also use the X variable there as well. R is the growth rate. It's given to you typically as a percent, and you have to write it as a decimal. And then the percent of increase is 100 times that. So you're going to use the R as the growth rate as a decimal versus the percent. Then we also have exponential decay. Now, when we were graphing these, we had A times B to the X power. But in this situation, that B value is going to be a decay factor now, because it's going to be less than 1, but it will still be positive. So if you remember from yesterday's notes, the B value has to be less than 1, but greater than 0. So that's how we can recognize decay. Other than that, the rest is the same. The A is still that initial amount or value. T is still your time period. R is still the rate. It's the percent that's written as a decimal. And then we go from there. Okay, so when we solve these problems, the first thing we have to decide is it exponential growth or decay, so that we know which formula we're using, and then we can kind of put in the appropriate information from there. So if we look at this example here, we want to look for a keyword that tells us, is this item or money or whatever it is going to increase and grow, or is it going to decrease or decay? So if we look at this first problem, you deposit $500 in an account. So you're putting money into an account, and it's paying 8% annual interest. And interest is money that you're making on your money. So this 500 would be our A value, and this 8% would be our R, and we would have to write it as a decimal. Now, if there's no decimal in your percent, wherever your percent sign is, you're moving a decimal from there over to the left. So in this case, you would be moving it 1, 2, and that's why I'm filling in that 0 there. Now, because this is growth, I'm going to use the equation A times 1 plus R raised to T. And my growth factor should be a number larger than 1 when it's calculated. So when I'm writing the model, when you're writing the model, you're just substituting in the A and the R. You're not putting in the T yet, because this is a model that can be used. You're creating a model that can be used for many, many values of T or X. So I'm going to have Y equals 500 times 1 plus 0.08 raised to T. And that can be simplified by adding up the numbers in the parentheses. 1 plus 0.08 will just give you 1.08, which makes sense that this is a growth factor because the number in there that's being raised to the exponent is larger than 1, which would confirm that this is growth. So now you can use this model to answer any questions related to different time periods. So What is the account after 6 years? You'll plug in a t equals 6. What is the account balance after 20 years? You can plug in a t value of 20. So using your calculator, you would type in 500 times 1.08 raised to, the first time period was 6, and then you get your answer. You can do it again with the 500 times 1.08, and this time raised to 20. You could continue to use that model for any amount of years and get an answer. Now the first one, remember, if we're doing money, you would want to round appropriately to dollars and cents. If it's not money, make sure you're rounding appropriately, labeling your answer. So here's $793, and this would round to 44 cents. So $793 and 44 cents. And then the 20 years is $2,330 and 48 cents. Okay, so let's look at the next problem. Okay, the population in a town has been declining. So this tells me this is probably going to be a decay problem. The rate of decline is 2% per year. So that means my R is going to be 0.02 because there's no decimal. So I'm taking my percent, moving it over 2 spots, filling in that 0. And the population started out as 84,223. So that's my A value. So my formula that I'm using is A times 1 minus R raised to T. So I'm writing my model. That would be Y equals my A value, which is 84,223, times 1 minus 0.02 raised to T. And I can simplify that by doing 1 minus 0.02 on my calculator. So if I did 1 minus 0.02, I have 0.98. And most of these are simple enough that you can do without a calculator. Now this is my model. I can now use that model to solve any time period. So what's the population in 2006? Now remember, the initial population was from 2001. So 2006 would be 5 years later. So that T would be 5. In 2016, that's 15 years later. So you're going to use a T value of 15. So then now you'd go to your calculator and plug this in. 84,223 times 0.98. And we're raising that to 5. Whoops. Sorry. Hit the wrong button there. Okay. Sorry. Let's start over here. 84,223. Okay. All right, much better. So we would have 76,130.9. Now you can't have 0.9 of a person, and this is population, so I'm going to round that up to 131. 76,131. And this would be people. And then we do the 15. And we do 84,223 times 0.98, and then we're going to raise that up to 15, giving me 62,200, and that's going to round up to 5. And again, people. Okay. All right, next question. We're talking about buying a used car for an initial value of 18,000. So that's my A value. The value of the car will be less each year because of depreciation. So that's telling me this is a decay problem. The car depreciates or loses value at a rate of 12%. So my R is going to be 0.12. So to do my model, I'm putting in my A value of the 18,000, followed by my decay factor, which would be 1 minus that rate of 0.12. Now I can simplify that to finish getting my model. 1 minus 0.12 is 0.88. This is the model that I'm now going to use to answer any follow-up questions. Estimate the value of your car in 8 years. So I'm going to put in a T of 8. So what do I get there? So on my calculator, 18,000 times 0.88 raised to 8. And it's valued at $6,473.42. Okay, next question. From the year 1982 through 1997, the purchasing power of a dollar decreased by about 3.5%. So my initial value is just $1. And my rate, this time, there is a decimal here, so I'm moving the decimal 2 spots, and I'm going to get 0.035. That's a very common mistake. A lot of people will not move the decimal appropriately. Okay, so write a model for purchasing power. So it did say it decreased, which tells me this is the decay model, which means we're going to have to do 1 minus that R. So my A value is 1, and then I'm doing 1 minus 0.035 raised to T. So I can simplify that. If you go to 1 minus 0.035, we're left with 0.965 inside here. That was my decay factor. And now I can use that model to figure out what the purchasing power is in any given year. So using 1982 as the base, what was the purchasing power in 1997? So if you subtract those years, 15 years have gone by. So you're going to go put that in for 15. So 1 times 0.965 raised to 15. And we get 0.586, which would be 59 cents. So that would just mean that later, your dollar only gets you 59 cents. It's like having 59 cents. That's all you can buy with it compared to what you would have had back in 1982. Okay, example 3. A population of 20 rabbits is released into the wildlife region. The population triples each year for 5 years. Okay, so we know that there's a growth happening here. We know the A value is 20, but the rate is a little bit more confusing here. It doesn't give you the rate. Instead, it's telling you that the population is tripling. So really what they're giving you here is the B value, and it's going to be a 3. And that's because this rate was actually 200%. So I know it's weird, right? But if I increase something by 100%, I'm doubling it. So, if you have 1 pizza, or let's just say rabbits, right? If you have 20 rabbits and I double that, I've increased it by another 20, which was 100% of what you had. If I increase it by 200%, 100% is 20, 200% would be 40. If I increase 20 by 40, I now have 60, which is tripling. So it's a little bit confusing, but if you just think about that as the B value, it's actually the growth factor. You can just put it in that way. So now it says, what is the percent of increase each year? The percent is actually 200%. And then your rate would be, it's just actually 2. So when you put it into the model, you have A times 1 plus 2 raised to T, which of course gives you that 3, which is kind of like the tripling. And then we want to put a 5 in for the T. So 20 times 3 to the 5th power. And 4860. This one is already rounded for us. which is good because we can't have a fraction or decimal of an animal. Okay, and finally, number 4, a newly hatched channel catfish typically weighs about 0.3 grams. So that's going to be our initial A value, or what we're starting out with. During the first 6 weeks of life, its growth is approximately exponential, increasing by about 10% each day. So my rate is 0.10 because the percent changed to a decimal. And we know that it's growth because we see that it's saying growth in here. So write a model for the weight during the first 6 weeks. Okay, so we have our model, y equals 0.3 times 1 plus 0.10 raised to t. Now I want to simplify. So I have 0.3 times 1.10 raised to t. Now, you want to put your t in. It says find the weight at the end of 6 weeks, but t is not 6, okay? The reason is because here it said that it grew 10% each day. So we need to have the t in days. So 6 weeks times 7 equals 42 days. So that's going to be your t. So you're going to do 0.3 times 1.1 raised to 42. So that's what we need to do. So 0.3 times 1.1 raised to 42. And this will give us our weight, which is 16.429. So I'm just going to make it 16.43. And that would be grams.